Okay. So
Okay. So, so, okay.
okay, second. Okay. Okay. So let's get started. So welcome to this third class on statistical mechanics. And this is a class that I'm taking as a part of my TA course for PMRF. And I'm Sauravi from Indian Institute of Science. And in the last two classes, we have been discussing about thermodynamics. And we discussed how one can define different thermodynamic potentials, the state functions, okay, what are what is the macroscopic description, what is the microscopic description, and how thermodynamics comes as a more of a phenomenological description of the macroscopic system, right? Now, from now onwards, we would gradually move towards statistical mechanics, which is more of a probabilistic approach, if you remember. It's a probabilistic description. So, for this, in today's class, we would spend some time understanding different probability distributions, okay? And how are they characterized? What do you mean by moments of different distributions, cumulants of different distributions, okay? What do they signify? And then we would also talk about the most well known or popular, you know, some of the well-known distributions, probability distributions, and also use them in understanding how one can solve random walk problems, which is a very standard problem that comes up in statistical mechanics, right? Now, before that, needs to understand why we are talking about probability, and we will also discuss about that as we proceed. Okay, so like the other classes, this will also have second. Why is it not changing? Uh, so there's some lag in the. Just 1 minute, guys. Is something wrong? I'll stop sharing and then I'll reshare again. I don't know what is wrong here. 1 second. Yeah. Okay. So as we, you know, did in the other two classes as well, we'll talk about some basic concepts, okay, which will be used for problem solving. So we'll discuss the basic concepts and formulae, and then we'll try to solve certain questions. And if there are any doubts from your end, you can let me know. Okay. Oh, I don't know what is wrong. Okay. So now the basic concepts. Now, why are we discussing about the probability distributions and all that, right? Why is it coming up in this discussion of statistical mechanics? Is because one needs to understand that we did discuss the two descriptions, right? One is a macroscopic description, another is a microscopic description. Now the macroscopic description talks about certain variables for the whole system, right? Or a more coarse grained description, so where you have temperature, pressure, volume, and so on. And thermodynamics, what we had been discussing was mostly equilibrium thermodynamics, where we talk about equilibrium properties of macroscopic system. And there, as you did see, that is more of an average kind of approach, right? We don't care about the behavior of the individual particles that are there in the system, right? Now, there can also be a microscopic description, which comes in terms of the position and the maybe momentum of the particles, right? Now, as we also discussed in the last class, now this, looking at individual position and momentum of all the individual particles in a system does not make, sense, or is not very useful, right? Because what matters is some observable or something, and we want to link it to that. And there, what matters is the inherent probabilistic description. Okay, so what do I mean by that? So if you have multiple microstates corresponding to a certain macro state, okay, now what is the description of individual microstate? Okay, how different, that is not important. What's more important is if you define us, so what is the probability of, being in a certain micro state, and how is it linked to the overall macro state, right? So that probabilistic description is what matters, right? So if you choose a macro state, what is the probability of there being different microstates corresponding to that one macro state? Okay, so it's inherently probabilistic, right? So in order to study statistical mechanics, one needs to have a basic idea of what probability is, how is it calculated, what does it mean, okay, what are the basic properties or characteristic features, or how do you define different, uh, you know or characterize different probability distributions, right? So that's the aim of what we are going to discuss now. Now, when we talk about probability distribution, one needs to know what is a random variable. Okay. Now, what is a random variable? So, if you define a certain event, or suppose if you're talking about tossing a coin, then this the event of tossing a coin, okay, is associated with some random variable, which is whether do you get a head or a tail. So that's your outcome for that random variable of the event of tossing a coin, right? Now, random variables can have discrete outcomes like the one for the tossing of the coin, or throwing a dice, but then it can also be continuous. Okay, especially when we're talking about, suppose, velocities of particles and things like that, right? So there it can be continuous. Now, for any event E, there are certain features of probability, distribution or probabilistic description, which says that P of E for any event, okay, whatever event you choose, now P of E should always be greater than equal to 0. That is, all probabilities must be real and non-negative, okay? And if you have two disconnected events, then the probability of either of them happening, so P of A or B, is the summation of the probability of A happening and the probability of occurrence of B, right? So that's the additivity criteria. And then if you look at, if there's some random variable where all the outcome belongs to some sample space S, then the sum of all the possible combinations, the probabilities of all the possible combinations should add up to 1. That's the normalization, right? Now, you can define probability by different functions. Okay. So some of the descriptions are like you can have a cumulative probability function, which defines, so if you have some event E, okay, whose outcomes, belongs to uh, some sample space, and where these outcomes are defined as maybe X. Okay. So then the probability that your event results in an outcome which lies from minus infinity to x. Okay, this probability is defined as P of x when we are talking about cumulative probability function. Okay, while if you define probability density function, then we are looking at what is the probability that your outcome lies between x to x plus dx. Okay, so that's how you define the two. Okay, that definition also describes what are the different features. We'll just come to this. probability distribution, when we talk about it, if we talk about density function or if you talk about cumulative probability function, they will have slightly different behaviors, right? Because their definitions are slightly different. Now, for any function fx, if you want to, so there's some random variable x, okay, it has some probability distribution p of x. Now, if you want to find the expectation value of any function of this variable, some f of x, how do you do it? So you do an integration of fx px dx. So this px, or you can like here it's written as px, or even write it as rho x. So these would also mean, and then you do an integration from minus infinity to infinity. So that would give you the expectation value. I think somebody just write. Okay. So what we are discussing today is the probability, the concept of probability and the different distributions of widely used probability distribution functions. And why we are doing it is because that this idea of probability lies at the heart of statistical mechanics. So we are trying to now bring in the connection between thermodynamics, which was more macroscopic, and then the gradually we'll be talking about different ensembles and different kinds of descriptions. So we are not now trying to link the two. And for that, we need the probabilistic description. So you're looking at basic features of how one defines probability and how to characterize them. Okay. Now, this can be one of the questions which highlights how cumulative probability function can be different from a probability density function. Okay. So suppose for this question, which says that, which among the following is a cumulative probability function? So if I ask this question, will you be able to answer? So I see there's Satish here. Uh, would you like to answer to this question? Or any idea why it is a very straightforward question if one just knows the definition of what a cumulative probability function is. Okay, so let me just break it down for you. So basically, when we talk about cumulative probability function, that means we are looking at probability from minus infinity to that point, right? So that means this should always be a monotonically increasing function, okay? So which is something like this, right? So probability of infinity or 8. So if you have a infinite region or sample space, then you can take p of infinity. That should come out to be 1. And p of minus infinity should be 0, right? So it should be a monotonically increasing function which should flatten out at 1. So this is a typical plot of a cumulative probability function. Okay. Now, this same distribution can also be written in terms of a probability density function. Okay. And then what you get is something like this, right? So this is a probability, cumulative probability distribution. This is a density function. Okay. Now for density functions, they, so what is the requirement of a density function? So our density function should always be differentiable and integrable, right? It can have discontinuities, which we will see as we proceed, but it should be differentiable and integrable. Okay. So that's how you define or you see whether your density functions are making sense. Okay. Now, this is quite an interesting question, and this can, come up as different numericals or different in different contexts. Now, it says that the probability density function of a random variable x is given as p of x as this, right? So that means you have a random variable and you know the p of x, okay? So you know the random variable x, you know the probability density function. So no, typically when we talk about P of x, we are mostly talking about the density function. Okay. So P of x is given as this, and it says that now the given function in x, there's a new function f of x given as x squared, and we want to find what is the probability density function associated with f of x, right? How to do this? So you have one variable, you know the probability density function of that variable. Now there is a new function of that variable. You want to find the PDF for that particular function, fx, right? So the hint is that that means, so suppose when you say that you want to find the PDF of fx, what you want to find is what is the probability that fx lies between f, some small f, to f plus df, right? Now, this value of fx being equal to f will correspond to different values or can correspond to multiple values of x for which fx is equal to f. What I mean by that? So what do I mean is that suppose for this expression, if you take fx equal to 9, so you want to find what is the probability that fx becomes 9. Now we know that fx would be 9 either when x is plus 3 or x is minus 3, right? So now what do we have to do? We have to say that, okay, so there are two chances, two possible values of x for which fx becomes 9. One is plus 3 and one is minus 3. And we know the occurrence probability of occurrence of 3 and minus 3 can be defined from this expression, right? So we will use this probability and we will look at the different options of x which gives fx equal to 9, okay? Add them up and that would in a way give us a probability of fx, right? Understood, right? So the probability of fx being equal to f corresponds to the probability or corresponds to considering the fact that there are multiple values of x, each with different probabilities, okay, which would result in fx being equal to f. We have to use that, right? So how to do this? So you say that now your fx is itself a random variable, okay? You want to find pf of f df, okay? So basically probability of fx lying between f to f plus df. Now there can be multiple solutions xi to the equation fx equal to f, right? All the possible solutions. So for the example that I gave, your xi can be plus 3 or minus 3, right? Now, so what you can write is pf of f df is nothing but summation over all the possible values of solutions of x, and then you multiply p of xi into dxi, right? So from here you can rewrite pf of f as summation over I p of xi dx df at x equal to xi, right? So if we look at an example, you would understand how this is coming up, right? So that means here fx is x squared. So there are two solutions to fx equal to f, which is located at fx located at x equal to plus minus root over of f, same as plus minus root over of 9, that is plus or minus 3, right? And how do you define dx df? So now x is given as plus minus square root of f, right? So you can define, you can write dx df by doing a derivative of this, right? So that will give you the Jacobians, which is plus minus f of minus half by 2, right? So now what do? You just substitute it here, okay? So pf of f is lambda by 2 into e to the power minus lambda root f, which is nothing but p of xi, okay, from this definition. And then you are actually doing a summation over all the possible values of xi, where xi can be plus or minus root f. So you just substitute it here, and this is the form that you get, right? So now this is your new probability density function. Clear? Now, if you plot it, this is your probability density function of x. This is your probability density function of f. So you can see that there is a discontinuity at f equal to 0, right? But it's still a valid probability density function. Why? Because it is integrable, right? Okay. Okay. Now, once you have a probability density function, how do some notification coming? I don't know. So once you have a probability density function, okay, now you can define the different moments of the probability density function. Okay. What do you mean by moments? So that is nothing but expectation value for powers of the random variables. So nth moment will be written as expectation value, means integration of that quantity into the PDF of x, like P of x dx, integrating from minus infinity to infinity, right? That's your definition of a expectation value. Okay. So now expectation value of x to the power n, this will be termed as the nth moment. Okay. Now, in many cases, explicitly solving these integrations can be time taking, right? So there are easier ways of defining or calculating the moments. How to do that? One of them is this, is the way of finding the characteristic function. So the characteristic function is called the generator of moments. Why? Now this characteristic function is the Fourier transform of the PDF. How do you do a Fourier transform? You do an integration of that quantity into e to the power minus ikx dx, right? From minus infinity to infinity. So this is your definition of Fourier transform of your uh, PDF. And if you look at it closely, this is also the expectation value of e to the power minus ikx, right? Now you can again recover the PDF by doing an inverse Fourier transform. Okay, so again from pk, okay, you can again write it as px by doing an inverse Fourier transform. Now, because of this definition, so on one end, the characteristic function is the Fourier transform of the PDF, and this also means it's the expectation value of e to the power minus ikx, right? So you can do an expansion of this, exponential function, and you would get something like this, right? So that means once you have the expression for the characteristic function, you can compare, right? So you can compare the coefficients of k to the power n. Once you have pk, if you compare the coefficients of k to the power n, you would be able to generate the moments, which is given by this, right? X to the power n. So moments of PDF can be found like this. Now, if it is about some other non-zero value, then this will just be, accordingly changed, right? So you would have a x minus x0 to the power n term. Now, one can also define a cumulant generating function, which is the logarithm of the characteristic function. Okay. And this is how it looks like. So one can define a PDF in terms of moments, or they can also define in terms of cumulants, or you can also write the moments in terms of cumulants and vice versa. Okay. So as you can see here, so the first cumulant is equal to the mean or the first moment, right? The second cumulant is equal to the expectation value of x square minus the expectation value of x whole square, right? So this is the definition of your variance, right? Similarly, you can have x3. This is the third cumulant, or this is the fourth cumulant, right? And you can also rewrite the moments in terms of the cumulant. So you can do or express it either ways. Now, when you are writing the moments in terms of the cumulants, you can, this is just for you to understand and remember better. This just depends on, you know, looking at how you can group things. So when you say, suppose X3, you have three particles. So now you can group them in a group of three, or you can have, group them in group of one and two. and you can do it in three possible ways, and you can also keep them separately, right? So that's how this coefficient 3 can come up. So that's just a way of remembering how you can write the moments in terms of the different cumulants, right? Now let us look at some of some examples of probability density functions and calculate the different moments or the characteristic functions and so on. It's a very good practice. So whenever you go through this video, I would urge you to try to solve it yourself so that you get used to solving this kind of questions. Okay, now this is your p of x, the pdf, the probability density function, right? Now you want to find the characteristic function. What to do? You have to do a Fourier transform, right? So Fourier transform is defined as you do an integration of this with e to the power minus ikx from minus infinity to infinity, right? So this is just typical integration. So the integration has been divided into two, minus infinity to 0, 0 to infinity, typical uh, integrations. And what do you get out of it? So now what you get is, so this is your f of k or p of k, okay? And you get it as a series of certain terms, each of which has this powers of k, right? Now by comparing this with this form, right? So if you just compare or just look at the coefficients of the k to the power n, that will give you the expression of the moments, right? So that means this is telling you there are no terms with odd uh, powers of k, right? Which is telling you that all the odd moments will go to 0, right? So that means mean will go to 0 for this. And if you want to find, because mean is 0, now you want to find, suppose, the second moment. How do you do it? So you just first have to look at, you know, what is the coefficient of k square, right? So if you look at the coefficient of k square, that will give you the expression of the variance. So of the moments first. So first is moments, right? So you're finding the first moment, the second moment. So be careful about this, how you are defining the moments and the cumulants. Okay. So variance is the second cumulant. Clear? Okay. Now this is a very well known probability distribution called the normal distribution. Okay. Now, whenever you have a normal distribution, this is how the typical form looks like. Okay. Now, those who already know about normal distribution, you can just directly look at it and say that, sigma is the standard deviation, lambda is the mean, right? But let us look at how do we reach to those values, right? So if now this is your probability distribution or density function, you can find the characteristic function, okay, just by doing a Fourier transform. And typically, this is how it will look like. Now, because you have e to the power this term, what might be much easier to calculate is the cumulant generating function, which is just the taking the logarithm of p of k. Okay, so that would give you, so ln of p of k will give you this form, which is your cumulant generating function. So now if you compare this, compare the power, the coefficients of k for the different powers, that will give you the different cumulants. So what is this giving you? That the first cumulant is lambda, right? Now the second cumulant is sigma square, right? And all the other cumulants are 0 because you only have k and k square term. Clear? Now, once you know the first and the second cumulant, now you can write the different moments in terms of the cumulants. Okay, this is just by using this forms or this forms. It's both are the same. Okay, so once you know the cumulant, you can write the moments in terms of the cumulants. So in this case, so be careful about the fact that when you are comparing, okay, suppose this is a series, right? Now you have to compare it with the basic series of e to the power ikx, basically this form, right? So that's how when you compare, you get the right coefficient. So here for this case, you would have for k squared term, you would have a 2 factorial here, right? Now here you have, here there is no 2. So that already tells you that your moment, or should have a 2 here, so that the 2 and 2 gets cancelled, and that's the reason why you don't have any 2 here. So this expansion should be compared with the expansion of e to the power ikx. Okay, like this form. Okay, so similarly, then once you know the cumulants, you can write the moments, and these are the different definitions. So you can see that for normal distribution, only knowing the standard deviation and the mean is sufficient to define the system, because your entire system is described by only two cumulants. Okay, other things are not necessary. Okay, now that was about normal distribution, which is a continuous distribution. One can also have a binomial distribution, which is more of a discrete distribution. Okay, now this is a very well known discrete distribution, which is widely used when we talk about random walks and stuff like that. Okay, so what is this telling us? That if there are two events A and B, so whenever, because it's binomial, we're talking about two events, okay, A and B, and each has probability of occurrence PA and PB. Okay, there are total n events. Out of them, how many n events do you have, or how many A events do you have, or how many B events do you have? So how do you find that? Okay, hello. So what we have been doing today is we are looking at different kinds of probability distributions. Okay, to get an idea about how one define different PDFs. Okay, and we are discussing the well-known distributions which are widely used when we talk about statistical mechanics. Okay, and out of them, we just discussed the normal distribution, and now we are talking about the binomial distribution. Now, this comes very useful when we are talking about, uh, you know, problems related to suppose random walk and things like that. Okay, and it's quite simple. Why it's binomial? Because there are two. We are talking about two events here, each with some probability PA and PB, and you can see that this is how it's defined. So, if you say that the occurrence of you know NA number of A events is given by this. So this is the probability of that occurrence. And here the first term, okay, this is nothing but the coefficient obtained from the binomial expansion of PA plus PB to the power n. And that's why it's called a binomial distribution, right? Now, once you know the expression for this form, like once you know the probability density description, now you can try to find the characteristic function. Okay. How do you find the characteristic function? So you basically do a Fourier transform of this quantity, right? Now, Fourier transform of this is nothing but doing or calculating the expectation value of e to the power minus I k n a, right? So in the discrete distribution form, the integration will be replaced by a summation, right? So that's why you have a summation from na going from 0 to n. Okay. Now, what you can do is you can just rewrite this by, grouping all the terms with power na and n like separately. Okay. And because we know that na plus nb will turn out to be n, so you can do that substitution here. So nb is written as n minus na. Okay. So this gives you the form as this. Now from here, if you want to find the cumulant generating function, which is the logarithm of this, you would get a term like this, right? Now here the first, this term here is nothing but the cumulant generating function for a single trial. So what this is telling you is that whatever you get for a single trial, Now, if you have n such trials, it will nothing but be the n times of that. Okay. So n into this. So ln p1k is the cumulative generating function for a single trial. Hence, the cumulants for n trials will be n times of that. So now if you look at one single trial, we know that the allowed values of Na is just 0 and 1. Okay. And the probabilities are PB and PA. Why PB? Because when Na is 0, that means NB is happening, right? So that's the probability of occurrence of B. So you have the probability of 0 being PB and 1 being PA. And from there, you can find all the different moments of that single trial, which is given as PA. So now, after n trials, one can define the cumulants as n into PA. Okay. Similarly, now when you have the second cumulant, you can write it as in terms of the two moments, right? NPA minus NPA square. Now you can take PA common, and this is how it will look like. Okay. This is interesting because here you can see that mean goes as proportional to n, which is your number of trials, while your variance also goes as n. So that means the standard deviation goes as root over of n. Okay. So that's the reason why if you have large number of trials, your relative uncertainty in the measurement goes down. Okay. Because error goes as 1 over root over of n. Now, the binomial distribution is so it can also be extended to multinomial, and then you would just have a similar form but with more number of terms. Okay. Now, an extension of the binomial distribution can happen and under certain conditions, and then it becomes a Poisson's distribution. Okay. So when does it change to Poisson's distribution? So a Poisson process is a radio is similar to a radioactive decay. So basically the features are here. So the probability of one and only one event in this intervals t to t plus dt is proportional to dt. So you can take this probability as something like alpha. So you say that between t to t plus dt, the occurrence of the event has a probability of alpha into dt. Okay. And for whatever time you have, you divide your time intervals to very small uh, time intervals. Okay. So that means you have large, so dt tends to 0. Okay. And for each of this time interval, the probabilities are independent of each other. Okay. So now one can say that the probability of observing exactly m events in some time interval capital T is then given by a Poisson distribution. So what are the two criteria? First is that for each of the events, the occurrence of the events are independent of each other in all the different intervals. And for each interval, you have an event which occurs with the probability given as alpha dt. So in an interval, there are two options. One is either the event will happen or the event will not happen, right? So then it again turns out to be similar to a binomial distribution. There are only two possibilities of happening, right? So you define that the event now occurs with probability given as alpha dt. So if you compare with the last form, now your p becomes alpha dt. Okay. And what's the other event or so it can either happen or not happen. So then q becomes 1 minus alpha dt, right? So then this for that particular event, it becomes or time interval, it becomes like a binomial distribution, right? So now you can have n such small intervals, okay, where n is quite large, or you can say that the individual dt intervals are too small, dt tends to 0, okay. So then you would define the characteristic function as something like this. So it again has the form similar to the binomial distribution, right? Now you can replace p and q, okay, and n is nothing but the total time interval divided by dt, which is the individual dt time intervals, okay. So this is how it looks like. So you can find, so if this is your p of k, how do you find the probability density function? You do a inverse Fourier transform, right? So if you do an inverse Fourier transform, this is how it would look like. It's just rearranging these terms, taking e to the power minus alpha So you have e to the power alpha e minus ik. So these terms you can take out, right? Only the dk terms are important. So you just have to keep a to the power minus I k terms, and then you have to do an integration. And this is how it would typically look like. So here, this form, if you see, this is nothing but an expansion of e to the power I k x minus m. Okay. So if you replace it here, this can be rewritten as a delta function. Okay. What is this telling you? That now your probability density function involves a delta function. That means you only have certain possible values of x. For other cases, your probability density function becomes 0. Okay. So you can say that the probability of n m events is written by this term here. So alpha t, see, alpha is again this probability of occurrence of the events. Okay. And m tells us how many events we are talking about. Okay. And this is the typical form of Poisson's distribution. Now from here, once you know the probability density function, or once you have this form, right? Once you know the, what do I say? The cumulant or the characteristic function. From there, you can actually find the different cumulants or the moments, right? And that turns out to be equal. So it says that all cumulants are the same for this distribution, and that is given as alpha into t. Okay. So now once you know the cumulants, you can write all different moments in terms of the cumulants. Okay. So that's how these are very well-known distributions. Poisson's distribution, binomial distribution, normal distribution. They are very fundamental distributions. There are also different other kinds of distribution, but the very idea of characteristic function, how one defines the different moments, okay, or how to go from characteristic function to PDF and vice versa. All these are very useful whenever you're talking about any probability density function. Okay. Now, based on what we have just discussed, let us try to solve certain questions. So these are some of the questions that typically come in competitive exams like, JAM, JEST, or NET and all that. So I just tried to take up some questions from there. Okay. These are just basically using the concepts that we have just discussed. Okay. So it says that there is a box of volume V with n number of molecules. And now you have divided it into two parts, two compartments. And one of the compartment, the smaller compartment, has a volume given as V by 3. And we want to find the variance of the number of particles in it. Okay. So any idea how to solve it based on what we have just discussed? So we have already discussed uh, you know, all of what is required to solve this question. But any idea? I'll just give you some time. If you have any idea, please share. So you can feel free to, if you want to write in the chat box, you can write, or you can also, unmute and share your ideas. So you had n number of molecules in a volume V. Now you are looking at a smaller compartment of that volume where volume is 1/3, right? So if you talk about one particle, initially for the particle to be there in the entire box of volume V was 1, right? But now that particle can either stay in this compartment or that compartment, and the volume of the smaller compartment is 1/3. So do you agree that now the probability of finding the particle in the smaller compartment is like 1/3, right? So that's the probability of the particle being in the smaller compartment. Okay. Now the question asks, what is the variance of the number of particles, right? So now you have to use the very idea of, the binomial distributions in a way. Okay. So the probability of the single particle being in the smaller compartment is given as one third. Okay, so that means P is one third. So what is Q? Q is 1 minus P, which is two third, right? Now for a single trial, the variance is defined as P into Q. So this is your variance for one particular particle being in the smaller compartment. Now you have n such particles. Okay, so then it becomes 2n by 9. So it's a typical question that involves the concepts of binomial distribution. Okay, now there can also be questions like this. So based on the question, you have to first identify what is the distribution that we are looking into. Okay, in most cases, it's a very standard distribution based on what we just discussed, right? Now, there it says that there are on average 20 buses per hour at a point, but at random times. Okay, so this random times, the idea of random occurrences, these are associated with Poisson distribution. Poisson distribution is something which also relates to radioactive decay, right? So this events happening with a very low probability, but at random times, then these things are associated with Poisson's distribution. Okay, so it says that there are 20 buses per hour at a point, but at random times, the probability that there are no buses in 5 minutes is closest to what value? Okay, so I can say that we have to use the Poisson's distribution in this question. But now, what will be so in the Poisson's distribution? What do we need? We need the number of events that we are talking about. Okay, now that we can very well understand that the probability of no buses, that means the number of particles or m that we were talking about, is zero for this question. Okay, another thing that we need is what is the probability of occurrence of that event, right? That alpha t, that term we need, right? So how to find that? That's already, we just have to do a, what do I say? A transformation like of the information that's already provided. So there are 20 buses per hour. Okay, so based on this, what is the probability of occurrence of number of buses for 5 minutes? That's a transition that you have to look into, right? And from there you can actually use the Poisson's distribution. So I'll give you a couple of minutes. Can you let me know how to do these questions? See, why we are trying to solve this kind of questions is just to get a idea about, you know, how to make use of PDFs. Because in the coming classes, we'll be completely discussing about the probability distributions, like, different ensemble theories and all this very idea where the entire concept of probability or probabilistic description is very important. Okay. So that's why in this class, we are looking into what probability is all about. Okay, and trying to solve some standard questions. Now, if there's anything that you don't understand, or if there's some doubt, you can just let me know. Or otherwise, you can just try to solve the questions based on whatever we had been discussing, right? So, would you like me to share the answer, or are you trying? If you're trying, we'll wait. Otherwise, we can share the answer. Okay, let me just share the answer and discuss. So for Poisson's distribution, this is how the distribution looks like for n events, okay, where the lambda tells about the probability. So what's the probability of the occurrence of the event? And then this is the number of events that you're talking about. So for this question, your n is 0. Okay. And here it says that there are 20 buses per hour. So that means if you have to look at 5 minutes, it's 5 by 3 buses in 5 minutes. Right. So now you have to just substitute here, putting n equal to 0 and lambda equal to 5 by 3. Okay. So that gives you the answer. Okay. So in this kind of questions, the first thing that you have to identify is the distribution that you have to talk or deal with. Okay. Now, the mean value of a random variable x with probability density given as this. So these are this kind of questions, in competitive exams especially, is very simple. Okay. But if you are not used to solving this question, what would happen is you would spend some time solving it. Okay. What do I mean by that? So you know the basic definition of finding the mean value, right? What will you do? You will use the probability density and then multiply it with x because you want to find the mean value of x, and you will do an integration from minus infinity to infinity. Okay. And now you will try to solve for individual terms, do a very lengthy integration if you are not careful about certain properties or certain what do I say, well-known identities of integrations that we're talking about. Okay. So just be careful. And that's why I just included this question. Otherwise, it's a very standard question. So if you do an integration, so you're doing an integration from minus infinity to infinity of x into px dx, right? So what do you think the answer should be? So if you know the identity or the property to look at, you would at once know what the answer is. Otherwise, you would be trying to solve the question, right? Any idea what the answer should be? See, I don't want you to solve the integration. That's the reason I have put the question here. Okay. So, because we can try solving it, it will take a lot of time. It's not necessary. Okay. See, the answer is zero. Why? Because it's an odd function that you are dealing with, right? So, in this kind of questions, one needs to be careful about these properties or these identities about integrations. Okay. So, you don't have to solve this integration. You can right away say that this is going to be 0 because you're dealing with a odd function. So, integration of an odd function from minus infinity to infinity gives you 0. Clear? So, that's the answer. So, for this case, the answer is 0. Okay. Just to remind you that in certain cases, you don't have to solve. So be careful. Okay. Now, this is another question which says that suppose we toss two fair coins 100 times each, the probability that the same number of heads occur for both coins at the end of the experiment is. So the first thing that you have to think about in this kind of questions is What's the event? The event is we are tossing two fair coins 100 times each. Now, this act of tossing one coin is independent of the other, right? So you can just find what is the outcome for one coin, and then you would have to just multiply it with the other because both are disjoint, independent events. Okay. So now if you toss one coin 100 times, what is the probability that you get some certain n number of heads? Okay. That's where you have to start. And then you have to proceed further. I'll give you another couple of minutes. Just see if you can solve it. You have to use the description of binomial distribution because you're tossing a coin which has two probabilities, either head or tail, right? So that's a typical binomial distribution uh, question. And then look at how many we are talking about. Okay, how many events? Do it for one coin first, and then the same will be happening for the other. So you can just multiply. They are independent events. So when you're talking about probabilities, if there are two independent events happening, you can multiply the two. Okay, if you're looking at a joint occurrence of two events. Extremely silent. See, yes, yeah, hello. Some noise. Okay, so let's try to work it out. Okay, so we know that this is how it is defined for a binomial distribution. There are where there are possibilities of like two outcomes possible, head or tail. So in this case, PA and PB for tossing a coin, fair coin, is half. We know that, right? So what you can do is PA is half, PB is half. Okay. What is N? N is 100 because you're tossing it 100 times. Now you can choose some NA, maybe that is small n. Okay. So if you toss one fair coin 100 times, then probability of n number of heads occurring at the end of 100 times is given as 100 Cn half to the power n into half to the power 100 minus n, right? So from here, you know what is the probability for one coin, right? Now the same probability will happen for the other coin, right? Now because it says that probably the same number of heads occur, now your small n can take any possible value from 1 to 100, right? So this should be 1. So 1 to 100, right? So that means you can just club them together. So 100 Cn whole square into half to the power 200, right? Now this term you can take it out, okay, and do a summation from n equal to 1 to 100, 100 Cn whole square. So that's your answer. So these questions are pretty straightforward, but it's quite useful to solve some of them, at least to get and remember the basic definitions of different fundamental distributions. Okay. Okay. Now, an important point about probability is conditional probability. Okay, this is something which we have at least heard at least once in our till this time, but I just found that it's interesting to important to at least remind you once about it, because there can be wide range of questions based on this. Okay, so it says that if there are two events associated with some same sample space, okay, the conditional probability of event E given that another event F has already occurred. That's the conditional probability. Okay. And that is given as P of E intersection F by P of F. Okay. So suppose there is a question which says that there are 10 cards numbered from 1 to 10, okay, mixed up thoroughly, and then one card is drawn randomly. If it is known that the number of cards drawn is more than 3, what is the probability that it is an even number? Okay, so what are the two events you're talking about? One event is that the card drawn is more than 3. Another event is that the card drawn is an even number. So there are two events that we have defined, right? And now it says that how do you define the probability that it's an even number when you know that the number drawn is more than 3, right? So that means there are two events, A, which is like all the even numbers, B, which is all the numbers greater than 3. So A intersection B, which is this number, right? So the probability then becomes, okay, P of A given B is P of A intersection B by P of B. Okay, so 4 by 10, which is the intersection. So 4 by 10 by 7 by 10. Okay, these are very simple concepts which we have read, I think, during our higher studies, like higher school studies. So, but this idea has a huge application or a lot of applications in problem solving. Okay, so just remember this is how you define conditional probability. Okay, now there is this total theorem of total probability which says that now if you have different events, okay, E1, E2, E3, many events, and they all correspond to one sample space S, and each of them has some non-zero probability of occurrence. Now there is another event A, okay, associated with the same sample space. What is the probability of occurrence of A? Okay, so a similar application came up in the second question when we were talking about probability distribution of f of x when probability distribution of x was known, if you remember, right? It had a similar concept involved there. So this theorem of total probability says that if there are different probabilities, E1, E2, all of that, each with some probability PE1, PE2, PEN, and then there's another associated event A. So for A, for each of the event E1, E2, E3, you can find P of A given E1, P of A given E2, P of A given E3, right? Dot, dot, dot. So then what is the total probability of occurrence of A? And that will be summation of this stuff. Okay. So we'll solve some questions so that we get an idea about it. Okay. Just remember this because later when we talk about even about, continuous probability density functions, these ideas will come up. Okay? And then there is this well-known Bayes theorem, which says that if there are E1, E2, n non-empty events, okay, and they are disjoint, pairwise disjoint, and they together, the union of all of them together is the sample space that we are talking about. And there is another event A with some non-zero probability, then the occurrence of EI, any event EI, when A has already occurred. So now it's the other way around, okay? P of EI when A has already occurred is given as P of EI into P of A. P of P is the probability. So probability of occurrence of EI into probability of occurrence of A when EI has already happened. Okay. And then dividing by the total probability of occurrence of A. See, this is nothing but total probability of occurrence of A. Okay. PA. So let us try to solve some questions so that we get some idea about how to address this kind of questions. Okay. So here it says that a box contains 100 coins, out of which 99 are fair coins and one is a double-headed coin. Okay. Suppose you choose a coin at random and toss it 3 times. Okay. So it turns out that the results of all 3 tosses are heads. What is the probability that the coin you had drawn is a double-headed one? Okay. So I'll just give you a couple of minutes to, like whenever you see the video, I want you to, spend some time and try to do it yourself. And then we would like look at the solution so that you remember how to do these questions. Okay. Like these are quite standard ones. So once you do it, it's just like a revision. You have already solved this kind of questions before, I hope, and I think you will have. It's just a revision to revise and keep things updated in your brain so that you know this is how it's to be done. Okay. First, for this kind of question, you need to write the different events that you're talking about. Define the events first. Okay. Then it will be easier to solve. So, what are the different events that we are talking about? So, one would be what is the probability of fair coin? What is the probability of double-headed coin? And then there's this event where you know, choose a coin at random and toss it 3 times. So, event of tossing a coin 3 times and the event that you are getting all heads, right? So this is the event that we are talking about, right? So it's something like this. So you can choose a event of fair coin. So P of E1 is known, 99 by 100. Then there's a double-headed coin, only one, so 1 by 100. Okay. Now what is event A? It is tossing 3 coins and getting 3 heads, right? Now what is P of A when E1 has already happened? Okay. P of A when E1 has already happened. That means you know that you have chosen a fair coin. What is the probability that you get 3 heads? Okay. That should be half to the power 3, right? That is 1 by 8. Now, what is the probability of getting 3 heads when you know that you have chosen double-headed coins? It's always 1, right? So once you know that you have chosen a double-headed coin, you know that you will always get head, right? So P of A when E2 has happened is 1. Okay. Now, you were asked what is the probability of finding or of you know probability that you have drawn a double-headed coin. So you have to find probability of E2, okay, when A has already happened. That means you have got 3 heads in 3 tosses. What is the probability that you have drawn a double-headed coin, right? So that means you have to use Bayes theorem, okay? And this is how it's defined, right? So all these terms are provided to you. You just have to substitute them to get the value. Okay. So if you are interested in it, you can also go through the maybe derivation once just to get an idea about how to. So this is very easy to derive them using Venn diagrams. Okay. But if you want, you can just look into it and get an idea. These theorems are very useful, especially when you're talking about, so suppose in later questions, when we talk about random walk and stuff like that, there also this ideas of conditional probability, Bayes theorem, total probability is very important. Okay. So if you now know all these values, so you can just substitute to get the answer. So this would be your answer. Answer is C. Okay. Now this is another question which says that a person plans to go from some, you know, point A to point B, and there are two different routes. So first you go via route R1, and then there are two possible ways, R2 and R3. Now there is a possibility that and each of them, the probability of taking this route is half. Taking this route is half. Okay. Further, there is a probability one third that R1 is blocked, and the probability one third that R2 is blocked, and the probability one third that R3 is blocked. Okay. What is the probability that this person will reach point B? That's the question. Okay. So it again, you know, takes into account. So you have to think which are the different events. Okay. Also think about whether the individual events, which of them are independent of each other. Okay. And then look at or bring in the idea of total probability as well. Okay. See, what is the so for you to go from point A to point B, your R1 initially has to be unblocked. If this is not unblocked, it's not possible for you to take any of the routes, right? So that means there is a possible, so the probability of this getting blocked is one third. So this has to be unblocked. Okay. Now, once this is unblocked, what happens? So that becomes unblocked by a probability of two third, right? So this becomes unblocked by a probability of two third. Now, once you are here, there's two options. So you can take this route by a probability of half, right? You can also take this route by a probability of half. Given the fact that R2 or R3, whenever you're taking any of the routes, is unblocked, right? Because there's also a probability that your R2 and R3 can also be blocked, right? So that means the probability that once you are here, you have taken R2 is half into again two third, right? Because the probability that R2 is blocked is one third. So it has to be unblocked. So 2/3 into the probability of half, right? And same goes here, right? Now, the act of taking this route and act of taking this route are independent of each other, right? But what you are talking about, the event comprises both. So first this is to happen, this has to happen, then this will happen, right? So that means you will have this multiplied, okay, this multiplied by this, again this multiplied by this, right? That's how you have to do it. So the probability that, one second, probability that R1 is blocked is 1/3, so R1 has to be unblocked, and that is 2/3. Probability of A and B, you know, A to B without hesitation is half. So that means root R2 probability will be half into 2/3, and root R3 will be half into 2/3. Okay. So this is your answer. So this kind of question. So what you had to point out is the event of taking R1 and then R2, or the event of taking R1 and then R3. These pairs R1 plus R2. So these individual events of taking R1, R2 and R1 and R3, they are independent of each other. Okay, right? And then you also have to use the additive factor, which says that you can either take this path or you can take this path. So then that, and the total from A to B will give you the summation of the two. So that's how you get to this answer. Okay. Okay. Now this is another question which says that, there's a electronic circuit with 10,000 components. Okay. And if everything is fine, we talk, so performs intended function successfully with probability of 0.99 if there is no fault. Okay. And if there is a fault, then it successfully performs with a probability of zero point 0.3. And the probability of having a fault is 0.05. Okay. Now, what is the probability that your circuit performs successfully? Okay, that's the question. You have to find X. So again, you have to first define the different events. Okay. And then from that different events, you have to look at what are the combinations. Okay. So one event given the other. Okay. All those combinations. And then use the theorems that we had discussed. Okay. So this is the hint that you have to use. Define what is E1, E2, En possible, right? And what is A that we are talking about. So for this case, A is that the circuit performs successfully, right? That's your A. So there is one event where you say that your what could be E1 and E2? E1 and E2 could be the two cases where either the components are not faulty or they're faulty, right? So now based on that, try to uh, solve the question. See, probability of no fault is 95 by 100 because the probability of having faulty components is 0.05, right? So probability of fault is 5 by 100, no fault is 95 by 100. The success rate when there is no fault is 99 by 100. Success rate when there is success probability when there is a fault is 0.3, which is 30 by 100, right? So now you can define this as E1, you can define this as E2. So this is A when E1 has happened. This is A when E2 has happened. So you know the first, all the four terms required here. So then you can find PA, right? So how do you get PA? By using this formula, right? This one. So for this case, if you multiply, you would see that the answer turns out to be 9,555. Okay, so that's the answer that you would get here. Okay. Now, an important part about statistical mechanics is getting this idea of random walk. Okay. Now, random walk can be in two dimensions as well, but it will get complicated. So we'll mostly talk about random walk in one dimensions. Okay. Now, random walk in one dimension is typically the binomial distribution. Okay. Because when you are moving along a line, that's your one dimensional random walk, you can either take a step to the right or you can take a step to the left. Okay. So if you say that the probability of taking a step to the right is P and taking a step to the left is Q, then P plus Q is equal to 1. Okay. And now you can take N1 steps to the right and you can take N2 steps to the left. Okay. So then N1 plus N2 will give you the total number of steps that one has taken. Okay. And you would use, so if you're asked, what is the probability that you have taken N1 steps to the right? Right. So then it's the typical binomial distribution. So you write it as NC N1, P to the power N1, Q to the power N2. Right. And this is how it looks like. So again, here if you are asked to find a mean, okay, you would use the concept that it is n times of what happens. So if there are n steps taken, it is n times of what happens when you just take one step. So for one step, you know that the mean is given as p. So for n steps, the mean would be given as n into p. Okay. Now that's for the step to the right. Similarly, if you are asked the mean number of steps to the left, it will be q into n. Right. If you want to find variance, it would again be given as NPQ. This is similar to what we had got for binomial distribution. Okay. Now, the standard deviation, that is the root mean square, will be given as root over of NPQ. Okay. Now, based on that, we can try to solve this kind of questions which says that consider an asymmetric random walk with probability P for a hop to the right and Q for a hop to the left. The probability for M hops to the right from total number of hops capital N is given by this distribution. That's the typical definition of binomial distribution. Now find the probability Pn of M for a total displacement of M after n hops. So now what it says is you have taken some n steps to the right, m steps to the left. It is asking what is the probability of m total displacement. Okay, so that means now you have to rewrite your n and m like these in terms of the total displacement. Okay, so since the total displacement is the difference of number of hops to the right and the number of hops to the left, okay, so that gives you m and n minus m in terms of total number of steps and the displacement. Okay, so this is how you can write it. So now you have to just replace n minus m and m, okay, here in terms of capital M, which is now about displacement, and n is the total number of steps. So for questions where you are asked that it comes back to the same point, then what happens? Then your m goes to 0. Okay, so this is how from the binomial distribution you can write it in terms of the net or the total displacement after n hops. Okay, so for p equal to half, okay, which is typically the case for a if it is a symmetric one where you have equal probability of taking left and right steps, then it would be given by this. Okay. So that's the typical definition or typical way of solving for random walk questions. Okay. Now here it says that there are two rungs. Okay. Start out together at the origin, each having equal probability of making a step to the left or to the right. Find the probability that they meet after each one makes n steps. Okay, and they take steps continuous simultaneously. Okay? So what it is saying is that there are two drunkards and they are moving from they start from the origin and they can take equal probability of step to the left and right. Okay, after n steps, what is the probability that they come to the same point? So for this kind of questions, you have to go from the absolute coordinate system to a relative coordinate system, looking at relative motion, relative distance between the two. Okay. So the relative motion corresponds to a 2n step, right? Because now you are keeping one fixed and looking at the other. So now there'll be 2n steps. Okay. Now that means you can rewrite this question saying that now the relative motion corresponds to 2n steps and the total displacement after 2n steps is 0 because they have to meet, right? So now we have to find therefore p of 2n 0. So you have to just replace in the last form, this expression that we just derived, like this form, you have to replace n by 2n, okay, and m by 2. So then this is your answer. Clear? Okay. This is another question which says that there is a random walker which takes a step of unit length in the positive direction with probability 2/3 and in the negative direction probability 1/3. The mean displacement of the walker after n steps. So again use the fact that whatever happens after one step, for n steps it's just multiple of n, right? So that means now p forward is 2/3, p backward is 1/3. Okay. So that means in one step the mean displacement is 1/3. So then what happens for n steps? Just multiply by n. Okay. So n by 3 is the answer. Clear? Now this is quite of a fun question to solve. It says that consider a random walk of on an infinite two-dimensional triangular lattice, a part of which is shown. Now, what is the probability of moving to one of the nearest neighbor sites? If the probability of moving to any of the nearest neighbor sites are equal, what is the probability that the worker returns to the starting position at the end of exactly 3 steps? So it's more of a there's no real formula to use here. Okay, just you have to use the information that is provided. So it's a triangular lattice. So you have to see what is the number of nearest neighbors at each point. Okay, and the fact that you have to come back to the starting point exactly after 3 steps would limit the number, or the possible directions that you can take from each point, right? So based on that, you have to try to answer this question. It's a fun question to solve, so I'll give you some. Which kind of questions are quite common in competitive exam? See at each point how many nearest neighbors do you have, and then see what are the possible paths that one has to take, so that at each step the number of possibilities of steps that you can take will reduce, because you have to come back to the starting point at the end of 3 steps. Okay, so use that fact. So I mean, see, you can just mark the points like this. So if you start from point O, you have different possibilities of taking the path. So how many nearest neighbors do you have? One, two, three, four, five, six, right? You have 6 nearest neighbors, okay? And you can go to any of them, right? So for this point from starting from point O to like the first step, you can take anything possible, right? So that means the probability is 1, okay? Or you can say 6 by 6, 6 upon 6, right? Now once you are here or you are here, what is the number of possible steps that you can take? So suppose if you are here, what are the steps that you can take? So that after the third step, you come back to O. You cannot take this step, right? Or here you cannot go beyond this. Here you cannot take this step. Anyways, like suppose you are here at point C, you cannot take this, because if you take this step, at the third step you cannot come back to O, right? So this is anyways telling you that at each point, so suppose point here, there are how many possibilities? You have come from here to here. What is the possibility? So you can either go here or you can go here, right? Similarly, for point A, you can either go to B or you can go to F. For point F, you can either go to A or you can go to E. For point E, you can either go to F or go to D. Point D, you can either go to E or point C, right? So that means now for the second step, you have 2 out of 6 possibilities. Right? Now, once you have taken that step, so suppose if you start from here, now you have taken this step, you came here, you have taken here. So for each of this point, if you have to come back to O, there's only one route, right? You can go from C to O, D to O, E to O, any one of the route. Wherever you are, you have to just go towards O. So that means for the last step, you have a probability of 1 by 6, right? So that means starting from O, you can go in any direction. Now, suppose you go to A, to come back to O, there are two choices. You can either go to B. So at point A, you can either go to B or F, right? Now, once you go to one of them, suppose you have gone to F, there's only one way going back to O, that is to O. Right? So then the total probability of coming back in 3 steps is given as 1, which is nothing but 6 by 6. Okay. So 1 into 2 by 6 into 1 by 6. So your answer is 1 by 18. That's your answer C. So that's how you can solve this kind of question. So now it's a two-dimensional problem. Now two-dimensional problems there can be many tricky questions as well. Okay. So I've not included much here, but you can look for standard books which will look into this in even more details. But the basic idea is to use the binomial distribution, okay, and use the fact that sometimes it will be asymmetric, sometimes it will be symmetric. The ideas of so again, see here, there's this idea of conditional probability or idea of total probability, the theorem of total probability, Bayes theorem. So these ideas do come up in all this kind of questions. Okay, so keep those theorems in mind, and then you're good to go. Okay. Thank you. I think this is it for today. What we did discuss today is mostly the fundamentals of probability. Okay, what are the different descriptions, how one can go how one can define a distribution. So if you talk about normal distribution, you need to know the mean and the standard deviation, right? That's what we just got to know. There are two cumulants, so those ideas are very important. So now it has wide applications. If you talk about later, if you look into the central limit theorem, even there you'll see that the normal distribution is a very fundamental distribution. Okay. And suppose if you're talking about white noise or things which are so the very idea of central limit theorem also brings in the fact that the so when you talk about Brownian, suppose you are looking at the distribution of particles motion or particles displacement in a Brownian trajectory, right? It has to be a normal distribution. Now, once it becomes active or once there are other factors coming in, okay, then the distribution starts changing. Similarly, you can look at so when you are dealing with noise, okay, so even there can be different kinds of noise, okay. So it can be dominated by Poisson distribution, it can be dominated by like white noise has a normal distribution. So based on what kind of noise floor you have in your suppose you're doing some sensing measurement or something, so based on whatever noise floor you have, your description of the noise might be important, and there these ideas of how one can define the different distributions would gradually become quite useful. So the very idea of distribution by itself is very useful, and then and one should know the basic distributions. And then if you're talking about statistical mechanics or the fact that you're talking about we are going to discuss the different ensembles makes it important for us to know the basic definitions and properties of probability distribution functions. Okay, so just maybe go through different types of problems and different definitions and details of it. Okay, try to solve for the moment calculations or the cumulant calculations at least once for few examples so that you get an idea about how to go from the characteristic function to the cumulant generating function. Okay, that will give you a practice of what to do. Okay, that will be useful. And random walk by itself is a very, you know, you can go to much details if you want to. So it's a very, quite, what do I say? So there can be a lot of, discussion on random walk. We just discussed a very basic idea, which is fundamentally from the Brownian, from the binomial distribution. Okay. So I hope this helps. Now, in the next class, we'll gradually move towards the statistical description, where the very idea of microcanonical ensemble and gradually canonical, grand canonical, all of them will be coming up. Okay. So if there's any doubt anywhere, feel free to reach out. You can write to me or, also ask me in the next class. So I think if there's nothing else, so then let us call it a day. Okay. I'll just keep it, this time. So I'll keep it on for some time if anybody has any comments or anybody. I'll try to, get used to this forms, especially the first two, three ones. Okay? And this is a very important point, the characteristic function. And whenever you have to solve integrals, be careful. Many cases, the idea of whether it's a odd function, even function, will simplify your integrations to a lot of, extent. So be careful and be smart about using those. Okay. Otherwise, you lose time unnecessarily, which makes no sense. I mean, just like this question that we were discussing. Okay. Anything else that I should say? This is also a very interesting question. There can be a lot of, questions like this. Even when we talk about, I mean, the going from one variable to another has a lot of, like, once you know the probability density function for one of them, how do you go to a probability density function of a function of that random variable? It's so you can try to look at. I think this was from Kardar most probably, so you can look at other examples as well. Like Mehran Kardar, there's a book, so you can look into it. I think that's it. There's nothing more to discuss as of now. If there's any doubt, can let me know. Okay. So yeah, thank you.